Well, thanks, Josie, and good evening, Chari. Hailing from Perth, Western Australia, which is pretty much the antipodes of Stony Brook. So it's midnight there, and my good colleague and friend has agreed to stay up all night. I did send around your your impressive CV, Chari, but let me just quickly go over it. You hold three degrees from the University of Wales in Swansea, as in the UK, and has been at the University of Western Australia in Perth for over 30 years. You're a named professor. You've supervised over 60 research students and 150 honors students, and has published over enormous 446 articles, reports on coastal oceanography, which include 168 peer-reviewed international journals. Chari, you're a champion of coastal physical oceanography in Australia, and especially the West Coast and the coastal Indian Ocean. It's a very interesting area. And Chari gave a talk to our Tuesday morning physical oceanography group on the tsunami that was associated with the Polynesian island of Tonga not so long ago. But what most people didn't know, in addition to the ocean tsunami, there was an atmospheric shockwave that propagated around the world and had sort of significant effects. And so that was very interesting. Today, Chari is going to talk about the coastal oceanography of Western Australia. So without further ado, let's all welcome Chari Pattiaratchi. Knows Stony Brook well. He spent part of a sabbatical here in the late 1980s. And remembers as well. So welcome, Chari.
Thank you. You're good?
Yep.
All right, so I'm going to talk to you about my backyard, which is pretty unique. So this is the southwest of Western Australia. I'm just here, and I'm going to talk about what happens on this coastline just over here. But I'm also going to show you some nice imagery, but also the way that we're, how things have panned out for me and what we do. It's very sort of different in a way to looking at it. So our main forcing comes from what is called the Leeuwin current, which goes from north to south along the west coast, taking warm water from the equator to the higher latitudes. And it's very different because we are on an eastern boundary current. We have southerly winds. We should have upwelling. We should have a big fishery, but we don't have any of that. But nature, rather than sardines and herring, has given us rock lobsters. So it's very different to way of the system that I will sort of explain to you. So a lot of people that I would acknowledge, and I'll sort of say how all of these have actually come about over the last 20 to 30 years or so. So this was an old one that I did, but what I want you to sort of think, I mean, I'm sitting upside down compared to you, but really the oceanography is completely upside down. What I'm going to tell you, and most likely, is rarely in many textbooks. And those textbooks don't actually touch of the various things or many of the things that I'm talking about. Now, over the last 30 years or so, I've written many proposals. So all of these various components, which is basically for infrastructure. I've been in the team which actually wrote the proposals, and it's about $500 million in terms of infrastructure, so buildings and research infrastructure, instruments, etc. And this is on the bottom is our new building, which has been there for about 3 years. Now, the reason I actually put that into say is that it's very different, because one of the main components of this is what we call the Integrated Marine Observing System. And this is a federal government program which has been going for 16th year now. So this allowed us to basically keep collecting data. And so the way that we've been doing research has been very different. You know, say if you want to write an NSF proposal, you would sort of think of an idea, you'll come up with some aims, you will develop a methodology, and then you hope that proposal will be funded, and then you go away and actually do the work, but maybe limited 2 or 3 years, and then you've got to think about writing another proposal. The lucky part that I actually found is that we've actually got this IMOS, the observing system, now going for 16 years. The federal government told us that we got money for the next 5 years. So in this system, we're collecting data without, you know, the only thing that we are specified to do, collect the data, make it available freely to anyone. And we actually then analyze the data and say, what is they're giving? So all the different components that we actually, I'm going to talk to you about, really interesting and unique, is purely because we had an observing system. I never wrote a proposal to actually understand different components that I'm going to talk about. Just because the data was there, we were able to analyze the data and come up with the conclusions. So a lot of these, we basically, part of IMOS gave us basically a step change in the way that we do investigations. So these are the, it's a national program. This is last year, 15 years, and I'm going to mainly talk to you about ocean gliders, which I lead and run for whole of Australia. We also run the ocean radar facility, and then satellite remote sensing that we have. So all of these basically goes into a data portal, and anybody can actually use the data free and even in near real time. So here's an example. This is HF radar. This is actually a little bit older. We've now extended the coverage further north than what we see here. And then you actually see here a very large eddy and overlaying on the satellite remote sensing part of the HF radar system. Now, this HF radar has been going for 12 years. So we had 12 years of continuous data from each one of those points that we have ability to understand. So it's not only that we're looking at processes, we can also see how those processes change seasonally, interannually. They're very susceptible to El Nino and La Nina events. So you actually do. It's really amazing that year to year, we have the same data and we find something very different. Again, the HF radar, you can see a meandering of the Leeuwin current and how we are actually covering this main region. So here is an example from the radar. You can see here is 11 years of data from 2010 to 2018. On the left, we have sea surface temperature. So this is a cross-shelf transect just of Fremantle. They show very clearly the seasonal changes, warm and cold in winter. And this was a marine heat wave during a La Nina year in 2011. And then when we actually go to the currents, you see also the seasonal changes. So red is going northward. So near the coast, we have a seasonally changing current. And then we have blue going south is the Leeuwin current. And these other red are actually large eddies which get stuck and stay there for a few weeks. That's the transect that I was talking about. So when we look at gliders, we basically operate gliders for whole of Australia. We're the only organization, same with the radar, that operate gliders around for Australia. So we have sort of almost 350 glider missions and around almost 25 years of glider days of glider data. Here is a glider deployment actually in the Great Barrier Reef that we did for promotional systems. So very much high resolution, high temporal resolution, and spatial resolution, and that allowed us to actually identify many processes. So here, just to tell you, you'll probably know that the west coast of continents are cold, California, South America, South Africa, but we don't. We have warm water coming from the Pacific, we have no upwelling, we're very windy. Perth is the third windiest city in the world, and we have very small tides, 0.5 meter tides, and they are also diurnal. Another main feature is that we have high evaporation. The annual evaporation is 3 meters. So all these red parts around Australia, that's 3 meters. And our rainfall is about 500 millimeters. So evaporation exceeds precipitation by manyfold. The winter mean heat flux is 800 watts per square meter, and that also has a very large influence on how the system works. So here's an example of heat loss from a beach. To give you the scale, you can see 2 people on here, but you see this very much in terms of the latent heat flux in the system. Now, based on the West Coast, so if you now compare, let's say, Fremantle, Cape Town, and Valparaiso, similar latitudes, our air temperature is about 5 degrees warmer than comparatively on the same latitude, and we also have double the rainfall compared to Cape Town and Valparaiso. A lot of these happen because of these mainly cloud bands. So here we basically have warm water coming from the Pacific, and these systems bring rain all the way to the southern part. Most of you probably have heard about flooding in Eastern Australia in the last 2 years, and is basically this high activity of these cloud bands, and people now call these atmospheric rivers. And this is a climatology we looked at of all of these parts as it comes through. So when we look at our system, as I said, we have the warm Leeuwin current flowing southwards and the Cape's current going northwards. You can see this cold water going all the way through. If I zoom into this area here, we have Rottnest Island. This is about 20 kilometers long. And we have a shelf, a mini shelf break from about 50 to 100 meters. And then we basically have a canyon, the Perth Canyon, and I'll talk about that a little bit later. So our current systems are that we have the Leeuwin current flowing southwards, the Cape's current on the shelf, and the Leeuwin undercurrent going deeper than about 300 meters going northwards. So in terms of forcing, we have many different ones. Tides are negligible. As I said, the winds, we have very strong winds, particularly during the summer in the sea breeze. We have coastal trapped waves, we have heat fluxes, no major freshwater input. Actually not true. I'll show you. We had some in the last couple of years, a lot of rain, and I'll show you some in there. And the ocean currents, we have very strong resonance effects, we have topographic effects, and then seasonal and interannual variability. So this is Rottnest wind. So here we basically have daily winds. You can see stronger winds in summer, so austral summer, so January to December to March. Then we have storms in winter, and then moving away through. So we normally talk about 4 different seasons in the English calendar, but in the indigenous, they actually develop 6 different seasons, and they match very clearly the parts that we're talking about in terms of the winds explanations. The wind field also has a very strong response to El Nino, La Nina. So here the blue is La Ninas and red is El Ninos. And you can actually see that during La Ninas, the system is a little bit stronger. But more importantly, the winds in terms of the direction, if you look at the east-west component during La Nina years, it's negative. So rather than have southerly winds, we have southeasterly winds, which is affecting the upwelling and the mixing in the continental shelf waters. So we have a sea breeze. We know how the sea breeze is operating, but a lot of the things that we don't know is that how far offshore does the sea breeze extend? So we often only look at one part of the system, but we want to look at, in fact, how the sea breeze fronts move both on land and offshore. So here we see the development of the sea breeze. This is around 10 o'clock in the morning. And then you can see here, this is from an atmospheric model, the sea breeze front moving offshore, and then very quickly moving offshore. So here starts around 9 o'clock in this location, and every hour is extends to about 200 kilometers offshore, very much far distance compared to the onto land. So the sea breeze, as I said, is one of the strongest in the world. Now we're also in the area that we have resonance. So in 30 degrees north and south, the inertial period is 24 hours, so which is also the same period as the sea breeze. So this is John Simpson's work, basically says if you have south, north and south, around about 30 degrees, we have this resonance system. So now with our radar, we can actually see how the currents change. So here, 1:30 in the morning, we have winds coming from the north. This is the wind vector on the bottom left. So the currents are basically moving towards the southwest. A little bit 3 hours later, as we go through, these winds will change. Now the Coriolis force will come into being. What you actually see is that there is a big clockwise movement of the currents through the 24 hours. But just like you have a pendulum, if you're moving, but every time this circle goes around, you actually have the sea breeze hitting it. So the inertial currents get enhanced by looking at the current system. So here we see the diurnal ellipses obtained from the radar. You see here in the deeper water, so more greater than about 200 meters, we have well-developed circular currents. And then, of course, when we come into shallow water, that is inhibited. Again, we have the major axes of the currents, larger in deep water and lower in the system. So what happens? So now I'm going to show you some progressive vector diagrams of 200 meters and what actually happens in this layer as we have this circular motion in the surface. Remember, we're going to go through the whole water column. So you have this circular movement of the water right through the water column because of this resonance. So in summer, every day, You have the sea breeze when it doesn't blow every day, but most days, and you actually have this acceleration through the system. Now, when we look at, and the Ekman depth here is less than 100 meters. So now we actually look at, here you see this is 500 meters. You see the resonance starting with the sea breeze, so positive, negative, and it's out of phase in here. As we go with time, this is getting deeper, and now you actually see that up to 300 meters, these currents and the circular motion extends because of the resonance. In fact, in here, it's a different one that I plotted, you can see it goes down to 500 meters. So the resonance effect starts off, and then as time goes on, the sea breezes are blowing every day, and you actually have deepening, and then 500 meters. So the wind-driven currents extend to 500 meters when you compare only about 100 meters if you think of the classical Ekman flow. Now, but then year to year, remember I said that you actually change year to year. This is wind-driven. So I showed you how the winds change due to El Nino, La Nina, and then you actually see how year to year. So this is February 2012, 14, very similar, but now you actually say 2018, there were many events of that resonance purely because of the forcing from the sea breeze. Now, then we want to look at what happens. We looked at the currents, and this is now the temperature. So here you see the sea breezes, and if you look at the black, this is an isotherm of 19 degrees. So you actually see you have almost 40 meters, this excursion of the thermocline every day due to this resonance system. And when we actually work it out, at midnight, the thermocline is high, and the midday, it's at low. And so now, if you had 100 meters, if you have a 40-meter shelf, what we're going to have is that this water, cold water, is going to keep going up and down on the coastline. So here again, we see this is at 200 meters. You see the resonance, and now you see these daily excursions are of the order of 50 meters. So now we want to look at the glider data, and the glider data showing here density and chlorophyll, and you can see that sometimes this is repeated across. Sometimes the glider, the higher density water is on the shelf, sometimes it's off, on the shelf, etc. Now, this is what happens during the day, and all of the others happens at night. So what's basically happening is that as the resonance happens, we have the excursion of the thermocline onto the shelf during the day, and then out at night. So this happens every day through when we have this system. Now, when we come to winter, there's a lot of heat loss. So we have this big band of very cold water at the coastline. And then this is one of the earliest ones that we actually saw in terms of CTDs. You can see this cold water here moving offshore, and this water was also higher in salinity. But we didn't actually look at it very much until we came along to look at the glider data. So this is a glider transect. You see the cold water on the shelf, and this water is extending offshore. But it's not only temperature, you can see salinity, you see density, because you have high chlorophyll, you have reduction in the dissolved oxygen, and we also have CDOM, all of the parameters that we measure in the gliders. So what this is happening is basically we have higher density at the coast, lower density offshore, and this density gradient basically drives this intrusion along the seabed. Call it dense water transport, just as you have in an estuary. So now we can look at the data. We have data year to year and also seasons. So this is the area that I'm talking about, 2 rocks. So you actually see that we have a negative density gradient. That means that this outflows will extend all the way through this year, at least at 2 rocks. So we also collect data around whole of Australia, and then we can also extend this. So we can actually say in summer, we have evaporation, high salinity, and then we basically have the system, but there is no, because strong winds, we basically have vertically stratified. The winds decrease in autumn, and then you actually see the outflow extending through the whole water column. And then you might have different components in here. You have storms, etc. So here you can actually see the extending the cold water much further offshore. And then we can also look at different regimes. If you have low wind, you basically have outflows. If you have onshore winds, so what's happening is that, of course, it's enhancing the outflow through the system. But if you have offshore winds, the more dense water gets moved offshore. Of course, it becomes unstable because you have higher density water, lower density water, higher density water above the lower, and then that will mix, and you will have a mixing system. The same way that you have tidal straining, etc., in an estuary, in a similar way, you have the same processes operating in the continental shelf. So when we look around Australia, we see a whole lot of different systems, and then I'm going to call these ROFI, regions of heat flux influence. We have, as I said, annual evaporation of 3 meters. And then because of this system, we basically have cold water on the coast. So we have a tidal range of 10 meters here, 2 meters here. Doesn't matter the tidal range, you actually have the whole system. Now this is 1,000 kilometers long, the same distance as Brest to Denmark. And you have this cold water going underneath and extending all the way through. And all of go around Australia, you see exactly the same features, cold water at the coast, and this is now sinking through all of these regions in the offshore. So, give you a challenge. I bet the same thing happened in Long Island Sound. So, challenge for you to go and find it. Happens in the mid-Atlantic Bight too. So, I'll put this for Malcolm. Island Wake. So this is Rottnest Island. You can see this cold water in the north. You see in the system. And then as the water comes through this deeper water, it's upwelling onto the shelf, and the cross sections show this cold water. We can actually look at the glider data. But we also have, obviously, models. We run ROMs. So in the summer, we have a system of currents going from south to north. And then in winter, we have the currents flowing southwards. And you can actually see the eddies being shed from this island, extending many parts of the system. So this is showing us on the left the surface currents and animation. The colors are temperature, and on the surface on the left and on the right is the bottom. So we have this cold water, which is sort of the start of the canyon, which can extend all the way through. And this is our sea breeze driven system. And of course, day to day, you might have warm periods. You can see the warm water coming through on the left. Our summer temperatures can go up to 40 plus. So we have periods, there you go, periods of high high temperatures on the surface. And then we actually go to winter, you see a very different system. Now we see the currents going from north to south. We have big storms. You will see here flow separation and eddies on the southern part of the island, both on the surface and the seabed. And then you might have different ways of the system. Now, a lot of these, you actually see little eddies. I call them peddies for petit eddies. Or I could also be to my surname. So we have these eddies, around about 20 kilometers in diameter. There's many of these. So we started looking at this in the radar. We could look at cross sections from the gliders and the moorings. But I'm going to show you what actually happens. So here, what we have is the Leeuwin current going southwards, the Capes current going northwards, and now you actually see there's areas of shear. And then that creates the shear, creates the vorticity. You might have an eddy. So here you can actually say 23rd of December, 6 days later, it gets bigger. And then even a month later, it's much, much bigger. So now I'm going to show you a time series. This is day 0, 16th January. Now you actually see the currents going southwards. And now the shear zone being set up. The eddy is growing. Remember, this is observations from the HF radar. So day 4, the eddy is getting bigger. Bigger. Day 11 is still there. And then what you actually have, this is the Rossby number in here. So just over 1, which generates that eddy. What actually generated it? So what we have is a period where the eddy diameter starts from 0, day 0, and then basically goes larger and larger up to 8 days. And then, so this system, this eddy, which is this one here, lasted for about 2 weeks. Now, how was it generated? It was generated due to this cyclone. Cyclone didn't come anywhere near, but the cyclone generated a shelf wave. So here you actually see the currents flowing southwards as the shelf wave comes out and then changes. This is the peak of the shelf wave, changes the direction, creates the eddy, and then that eddy will grow for another 2 weeks. This is the shelf wave from the water level. You can actually see it's about 60 centimeters moving along the coast, and that created that system. Different cyclone, again, created shelf wave. You can see the shelf wave here. This is our eddy system. And here, before the shelf wave, you see the shelf wave starting and then generates the eddy in the system. So we have these cyclones, which occur 1,000 kilometers away. They can't come anywhere near our system directly, but since the continental shelf wide 1,000 kilometers or more, and then they create these shear, creates the vorticity, and basically have this. So this is ocean color, chlorophyll, and they have a big effect in terms of moving the chlorophyll from the coast to the offward. A classic example of how these systems happen. This is a really nice shelf wave that we started. So Port Hedland all the way to Esperance. It's about 1,500 kilometers, and you can see the peak, how that is going through the system, and that creates the eddies of Perth. Perth Canyon, very much a scar in the ocean. This is the actual system. And then we can actually, when we through the gliders, you can see the upwelling of the water around the system. The importance of this is that there's pygmy blue whales actually are in the canyon. They consume 4 to 5 tons of food per day, krill, and we've actually found almost 30 of these whales at any given time. So 30 times 5 tons, about 150 tons of food that they eat. So the canyon is a highly productive system due to the different interactions of the current system. As we talked about the river outflows, so this started in last year. You can see these darker values are so this is without in summer. You can see we have these ridges. This is basically bottom, but during the river flows, you actually see the water. So this is last year. So our river mouths, you can see the swan, the water coming out of these systems. Fortuitously, we actually we sampled these fronts through the gliders. You can see here, as the glider comes in, you see the fronts with cooler, lower salinity, higher coral flow, higher CDOM, and higher turbidity water along those frontal systems. So opportunistically, we put more data. So we actually sampled in here, and you can see each one of these systems here. This is surface salinity. We basically ended up sampling that lower salinity water. And then you actually see the lower salinity water, high chlorophyll, high CDOM. A lot of people say, oh, you look at ocean color, is it sediments or not? So we went and collected plankton toes, or actually, when we looked on the microscope, they were basically blooms of diatoms. And then we actually see, this is interesting from our point of view, physics point of view, or vertical isotherms and isohalines in here, and something that normally we don't find for a river plume, very sharp changes in the vertical in the system. So, a quick overview. I could talk all day, but I'm happy to take questions.
Well, thank you, Chari. This is a very interesting, complicated, and different system. Could you talk a bit about you say there's not a big fisheries, you talked about the whale. I mean, how does this great variability in water properties, temperature, salinity, and upwelling, downwelling affect what, just in general, and the marine life? I mean,
okay, so we have upwelling, but the upwelling is very shallow. So virtually no nutrients are taken up, and whatever nutrients taken up comes up, gets taken up by the phytoplankton. But that phytoplankton biomass is not large enough to support a fishery, a finfish fishery. So from an oceanographic point of view, you can say, yes, there's cold water, but there is no major, so it goes to the, let's say, the first trophic level, but that's it. So don't have anything else.
Now you talk about cyclones. I know in Australia and New Zealand, a cyclone is what we would call up here a hurricane.
Yep.
So what is the frequency of hurricanes on the West Coast, and is it changing at all?
Yes. I just was reading one of my thesis of one of my students who basically looked at the cyclone image prevalence for the last since 1970. There is a very marked decrease in the number of cyclones hitting in our region. We normally have, and also that we have more cyclones during La Nina years because we have warmer sea surface temperatures. None of that relationships go through. In fact, in the last 2 or 3 years, we had hardly had a shore crossing cyclone. They are very rare now, where, 10 years ago, you would have 5 or 6 cyclones a year.
Wow, so that's a lot. We have a group.
A little bit frustrating when you want to do science and say, I want a cyclone, and that doesn't happen.
I know. Could you talk a little bit more, Chari, about your program or the national program about glider research, and just most of us know what gliders are, but you might just tell us a bit more about that. And we have a group here at Stony Brook who is we have one glider at the moment, but there's another one coming soon. And Charlie and Jack are on the call. So you just tell us about how the Australian glider program has developed, and you seem to have a central role in that.
Well, with all of the integrated marines, when we set it up, initially, we said that we're not actually going to duplicate expertise around Australia. So there would be only one group will run gliders. So that's UWA, and I head that group. So nobody else in Australia runs gliders.
Oh my, but how do you do that remotely? I mean, Australia is a huge continent, the size of the United States. So do you do all the technical repair or calibration?
Yeah, we have people flying. We send the gliders by truck. They can't fly because they're lithium batteries. So people actually fly and deploy and recover. We do all the piloting centrally here. And we've got people going. We do 30 to 35 missions a year.
My goodness. And so what sort of support team does that require?
We have 4 people.
And
one person basically deals with the data, so does the quality control data. She doesn't go out to sea at all. Her thing is to basically make sure the data comes in, and the data we have 2 technicians who prepare the gliders, and then we have 3 people, another person who can deploy and recover and pilot the gliders. That's it. And we've been doing that for 15 years.
Which company or glider? Are they all the same company, or?
We had Slocum's and University of Washington, the sea gliders, but we basically retired at the sea glider fleet because a lot of our work is on the coast. So we're basically looking at shelf, and the sea gliders were not really very good to, if you look at the Great Barrier Reef, we basically will deploy a glider for, let's say, 5 weeks, and if they don't go deeper than 40 meters. And the sea gliders can't actually do that. And also we didn't have enough continuity with the sea gliders because it went to iRobot, then it went to Kongsberg, but we basically made the decision. Initially, when we started, Slocum's didn't have a deep water component. So now they actually can go to 1,000 meters. So if we wanted to go, we can go to deeper water.
Charlie and Jack, why don't you tell Charlie a bit about your program?
We certainly look like neophytes by comparison. When everything is running well, we get 4 deployments of a month each per year with our single glider. Another glider is going to arrive in January or so. It will be equipped with a thing called a demon, which will listen to the sounds of marine mammals, particularly whales. So since you seem to have pygmy blue whales in the canyon. Have you deployed any of these acoustic devices on your machines?
We haven't actually looked at in the canyon, but in the north, when where we got humpbacks, we actually we put what do they call it? Soundtrack. It's a commercial company which was actually and we basically mounted it on piggybacked on the gliders, and that worked pretty well.
Right. Well, we're mounting Vemco fish chip listening devices on our single glider.
Yeah. Well, we all our gliders have the Vemco ones because we have not for looking at whales. We have a big program as part of IMOS, which is tagging fish, particularly sharks, and so we basically find lots of sharks. But on the other hand, that's also our biggest problem. We have lost many gliders due to shark attacks, so it cost me maybe $100,000 or $200,000 worth of shark damage to the glider fleet.
A year or overall? Oh,
yeah.
Yeah, well,
times of the year we don't actually deploy gliders in particular regions because it's too dangerous.
Oh.
Yeah, the last time, one of the times we deployed our glider, a shark swam around it, but the shark wasn't any bigger than the glider, so I think he probably decided that this was a losing battle. Anyways, he swam off. So we haven't seen any shark attacks. Although
all our gliders basically have big teeth marks everywhere. In the rudder, they've taken CTDs out, they've done everything. We've actually made 3 gliders as shore gliders with shark attacked gliders. They don't have instruments, just the covers. Right? And if you have a shark bite, we don't actually use it. We don't use that hull again because we cannot guarantee the integrity of the hull.
Well, as I said, we're beginners here. Their program is going to expand, but nothing like 30 deployments a year. Thank you very much. And it seems to me that you guys are rivaling Rutgers in terms of deployments per year and levels of expertise.
Yeah, we're almost the same. I mean, it depends on if you look at the glider days, scripts are actually way ahead because although they don't do that many deployments, their deployments actually last a long period. So their deployments are 3 or 4 months. Right. So if you count on glider days, they are way ahead.
Okay, well, thanks. This was very interesting. I don't know, maybe 40 years ago, I spent about a month on the Dampier archipelago. And one of the things I remember about it was that the salinity was just absolutely off the top. It was 40 parts per thousand or something like that. It was like being in the Red Sea. It was amazing.
Yeah, you never got to Shark Bay. The salinity there is 70. And last year, I actually had a record of measuring sea temperature. It was 41 degrees. So imagine a temperature of 41 degrees and 70 salinity.
Now, where is this place? Well, on the south coast.
Shark Bay. It's about 800 kilometers north of Perth. I'll be there next week, actually, next weekend.
Where all the stromatolites are.
Exactly.
Hey,
Signs of early life.
Kamazima has a question. Malcolm.
Oh, sorry. Just, yeah, if you have a question, just yell out. Kamazima.
Hi, thank you. Thank you, Chari, for a great talk. I have a comment and then followed by a question. My comment is on the acronym ROFI. it sounds too close to Rofi. So when you are talking, it might be difficult to distinguish between the two. Why don't you flip the letters around, become fro?
I actually don't use it very often. That I use it to tease some of the European friends.
Well, you kind of teased me. So my question is on the eddy being spun by the coastal trapped waves.
Yep.
And what is the interaction then that follows between the eddy and the coastal trapped waves? I would think.
No, so what you basically have, maybe I'll explain it a little bit better. If I'll share my screen in a minute. I'll get my. Okay, so what happens is that first of all, before I actually was doing this, I thought it was the wind stress which was actually changing and creating these eddies. But what happens is that when the shelf wave comes along, initially you can see here, this is along this transect, all the water is going to the south. So that's the crest going past. But after the crest passes the point, the transect here, on the shelf, the currents reverse due to the shelf wave. But in the deeper water, there is no reversal because we are now outside. This is the Leeuwin current, and we are outside the Rossby radius. So now you have shear of the continental shelf wave on the shelf and the southward flowing currents. So that actually creates the eddy. And this eddy then will keep growing after the shelf wave's gone. So the shelf wave is only doing that to initiate it. But after the shelf, it has been initiated, it basically keeps growing because there's enough, it sustains sufficient vorticity and creates it to keep growing.
I had a question also about this eddy. It was so perfect. It was so round. The question then is, but they only seem to last a couple of weeks. So what happens to them? Who eats them? Do they propagate away, or does something come through? And
well, if the system actually do, they propagate. They can detach and move offshore. Some of them last for up to 300 days. They go to the middle of the Indian Ocean. This is the most energetic eastern boundary currents in terms of the eddies.
They sort of like the Agulhas eddies head off to the west. So these are doing something similar?
Yeah, they go to the west. Yeah, they go to about 80. I mean, we are 115. The 80 is about the center of the Indian Ocean.
So Chari, sorry, I know there's other people wanting to ask questions, but couldn't it be the instability of the Leeuwin current that also might be triggering these eddies?
No, because the Leeuwin current is, these happen in summer, and the Leeuwin current is pretty weak during the summer months.
Okay, thank you.
Yeah, I had to pick different ones, and I have so many examples of these, so just didn't have time to show all of them.
Bob, did you have a question? You've popped up.
Yeah, I'm wondering what the nature of the shelf sediments are where the density excursions are so common. Are they sands? Are they muds?
It's very interesting. When I first came here, I was doing sediment transport, and a geologist told me don't bother to do sediment transport research because there's no sediments on the shelf. So I didn't bother for about 2 or 3 years, but really there is nothing. It's basically a limestone shelf, very hard, and so there is no mud per se, but it does have a lot of detritus. So there is a sort of broken seagrass leaves and kelp and all of that. So the sediments, if I look at my glider data, all of them have very high chlorophyll close to the seabed, because the light gets down there, and especially after a storm, it will actually resuspend, and then the nutrients, and then it will stimulate a bloom, and it will fall again. So very much on the continental shelf, if you put a grab sample, you might get a few limestone boulders, small rocks, if you like. That's about it, what you get.
Is there, do you think there's flow through the limestone the way there is through reef structures?
Very close to the coastline, yes.
Mhm.
I mean, we can measure the tide through the limestone. I'm saying the other way, maybe up to 1 or 2 kilometers inland. You can actually see the tidal fluctuations and more the shelf waves in the aquifer, maybe 1 to 2 kilometers inland.
Wow, that's great. Thank you.
So it's our time's nearly up, Charlie. Is there anybody else has a question? Just yell out. But I have one about tsunami warning system. Do you think when was that terrible tsunami that struck Indonesia, and when there was what 230,000 people killed?
2004.
2004, right? And there was a lot of frustration because there wasn't an adequate warning system in all the different countries and different languages. And I know that the folks at the Pacific system in Honolulu were very frustrated trying to get the word out that there was a catastrophe coming. And I think they even used like tourist handout materials of different coastal hotels and things to get the word out. What's the situation now?
Well, you talk very much about the Pacific. Do you know the history of the Pacific system?
Well, no, it goes back a long way. I mean, it's the oldest tide gauge in America.
I mean, well, a lot of the things that I'm trying to do now is that we are in a reactive society. We are not in a proactive society.
That's for sure.
So we may have incidents, we may have a disaster. We know it should have happened. We had the capability to do that, but we never actually do it. So I actually give the history of the Pacific one. So the first time they actually talk about a Pacific tsunami warning system was in I think it was in 1945 or 1946.
Yeah.
Nothing happened.
Yeah.
Then there's another tsunami, which was actually the big tsunami in 1960 in Chile. They said, oh, we should have a Pacific tsunami warning system. Nothing happened. In 1964, Alaska, Kodiak Island, then you have a tsunami. So it basically went 20 years before actually put into place, you should have a tsunami warning system. And now it was happening. And now we actually say in the Indian Ocean, 2004, we had a tsunami, 2005, 2006, we have a warning system, and that warning system works now. So if there's an earthquake, we will actually, everybody in the world will know whether there's a tsunami or not.
So is your university part of that system?
I set up the modeling part of that system for the Indian Ocean, yes.
Well, look, thank you, Charitha. This has been fascinating, a glimpse of oceanography down under. And it seems that it's alive and well. And your presence in Australia has made a huge difference to that vitality.